Let us now discuss the implementation of forwarding. So at every stage there is a choice of inputs for that particular functional unit. We can either use the default inputs from the previous stage, or we can use one of the forwarded inputs. So when there is a choice, we typically use a multiplexer to choose between one of the inputs. And similar to our control path that we had in the case of simple hardwired processor as shown in chapter 8, we'll have a dedicated forwarding unit that generates the signals for these multiplexers, which are called forwarding multiplexers. So this will be clear when we discuss the examples. So before the discussion, let's take a look at our forwarding paths once again. So we have 4 forwarding paths. We have one path from RW to OF, which is a long 3-stage path. We have two-stage paths, which are RW to EX and MA to OF. Oh, sorry, MA to OF is not required. We don't have it. We have two one-stage paths, which is RW to MA and MA to EX. Right? So basically, OF will have one additional path into it. EX will have 2 additional forwarding paths, one from RW, one from MA. And in the MA stage, we'll have one forwarding input from the RW stage. So we have a total of 4 forwarding paths. So now, let's now take a look at the OF stage with forwarding. So there is only one forwarding path which is coming into the OF stage, and this is coming from the RW stage. So what we do is that let's first consider the units of the OF stage. So the inputs come from the IFOF register. They are processed by the functional units inside the OF stage, and the outputs go to the OFEX register. So as we had discussed in the previous few slides and in the previous chapter as well, that there used to be one multiplexer to choose between the output of the register file and the output of the immediate unit. This is for the second operand, whether the second operand is a register or an immediate. So this was an original multiplexer that we had, so we still maintain it. In addition, we add 2 new multiplexers called forwarding multiplexers. So the first forwarding multiplexer M1, multiplexer 1, takes as its input OP1, which is the contents of the first register. So the contents in the RS1 field or the first source register, right? Its contents, 32-bit contents, and also the forwarding input from the RW stage, right? So we take both of these values as inputs and we choose one of them. And how we choose one of them, we'll discuss the logic later. Similarly, at the end of the other register file port, OP2, which gives us the value of the second source register, RS2, we also do the same. We have a multiplexer that chooses between the values, between the value of the register and the forwarded input from the RW stage. We choose between them, and so whatever we choose, we send it to the original multiplexer M dash, which chooses between a register input and an immediate, so the rest remains the same. And also we had discussed that in the case of a store instruction, it is necessary to essentially store the value of the second source register that we read. So that was stored in the OP2 field. So that is also there. So the only 2 additional changes that we make in this particular abridged diagram of the pipeline stage is that we only add 2 extra multiplexers, M1 and M2. So in M1 and M2, they help us choose between what the register file is giving us, which we call the default input, and the forwarded input that is coming from the RW stage. We choose between them, and if forwarding needs to be done, we choose the input that's coming from the RW stage. Otherwise, we choose what the register file is giving us. Let's now take a look at the EX stage with forwarding. So in the EX stage, what we do is that we mostly maintain the structure that we had. And so in the EX stage, what we had is that we had, so let's first see what goes into the EX stage. So three values go into the EX stage, A, OP2 and B. So A is the contents of the first source register. B is the contents of the second source register or the immediate, and OP2 is the contents of the second source register. So A, B and OP2 are what going to the EX stage. So we have been seeing this diagram for quite some time now. Now what we do is that we introduce two additional multiplexers M3 and M4, which are forwarding multiplexers. The forwarding multiplexers choose between the values A and B and the forwarded inputs that come from the RW stage and the MA stage, right? So one forwarding input comes from the MA stage and one comes from the RW stage. So both of them are sent to these three input multiplexers, M3 and M4. So both for M3 and M4, what are the inputs again? One input is that one input comes from the previous stage, which is the OF stage. Two more inputs come from other stages, the MA and RW stage. So based upon the forwarding decision, we choose one of these inputs as the output and they are sent to the ALU unit. Also recall that the value of the return address register needs to be sent to the branch unit. So the return address register is a valid register. So its inputs can also be forwarded. So we do that, and so the output of M3 is also sent to the branch unit, as should be the case, and the branch unit does its computation and sends the results to the IF stage. We add one more multiplexer M5 to choose between OP2, which is the register that the store instruction will use, and the forwarded input from the RW stage. So one trick question that readers can ask is that why are we not using the forwarded input from the MA stage? So that is very simple to explain. The reason we are not doing this is because we will actually require the OP2 value in the MA stage, right? So instead of doing an MA to EX forwarding, and it is much better to follow our previous principle that we forward as late as possible, and we forward it from RW to MA, because the instruction that is in MA in the current cycle would reach the RW stage in the next cycle, and the current instruction that's there in the EX stage would reach the MA stage in the next cycle, and in the EX, MA and RW stages instructions don't get stalled. So just in case the value for OP2 is being produced by the immediately earlier instruction, we can get it from the forwarding path in the next stage, right? So we will reduce one input, and also we will go by our self-declared principle, which is that we forward as late as possible. So that's the reason we add one more multiplexer over here, which is M5. So what the reader would have noticed by now is that adding forwarding to an existing pipeline is actually very, very simple. It's super simple, and the idea is very straightforward, that for every input to the functional unit, we add a multiplexer before it. So let's assume that this is the functional unit. We add a multiplexer before it. One of the inputs to the multiplexer comes from the previous stage, which is the default input, and the rest of the inputs come from the forwarding paths. So if there is one forwarding path, there will be one additional input. If there are two forwarding paths, there will be two additional inputs. Then we choose between one of these inputs and we send it to the functional unit. So that is the simple idea. So since there are two forwarding paths that come from the MA and the RW stages to the EX stage, every multiplexer to the input of both the branch unit and the ALU unit will have to choose one input among three. One of them comes from the previous stage and two come from forwarding paths. OP2 is an exception. The reason it's an exception is that it's not used in the EX stage, rather it is used in the MA stage. So we only need to consider one forwarding path, which is the RW stage. So just in case the correct value is there in the RW stage, we can forward it at this point of time. Because we can't forward it later, the instruction will leave the pipeline. And just in case the right value is there in the MA stage, instead of doing an MA to EX forwarding, we can do an RW to MA forwarding one cycle later. So this is according to our principle that we forward as late as possible, right? One cycle later. So let's now move to the next stage, which is the MA stage. In the MA stage also we maintain everything that was there in our previous pipeline. So we maintain all the structures that were there in the MA stage. We maintain the memory unit and the data memory, we maintain everything. Let's first focus on the inputs and then we shall discuss the new structures that we add. So the input is the ALU result, which is the address. So for a load, this is the only field that is required. And since this is pre-computed by the ALU unit, it will not be affected with forwarding. So it can go directly to the memory unit. In addition, since it's the result of the ALU, this is the beginning of a forwarding path. So when we are forwarding from MA to EX, it is this value which needs to be sent to the EX stage, because this is the value that the ALU has computed in the immediately preceding cycle. So we add a wire, the green wire, which goes to the EX stage. So this is the forwarding path. Alright, so let me maybe write it here. Okay. Now in the case of a store, we need to save the contents of a register into memory. So this we have been referring to the contents of this register as the OP2 field. So the OP2 field will be affected by forwarding paths. So what we discussed in the last slide is that instead of doing an MA to EX forwarding for the OP2 field, we can do an RW to MA forwarding because we want to forward as late as possible. So we will use the forwarding path which is coming from the RW stage and going to the EX and OF stages. And what we shall do is that we will add a set of wires between the RW forwarding path and choose the OP2 field which is coming from the previous stage, which is the EX stage, and the OP2 field which is coming from the next stage, which is the RW stage. So we'll add a single multiplexer, which is multiplexer M6. It's our sixth multiplexer, which chooses between these two inputs for the value that needs to be stored. This value is then sent to the memory unit, and in the memory unit the load or store happens, and the result of the load is sent to the MARW register. Recall that the store does not have a register result, so it will not produce any output other than writing to memory. The RW stage is very simple. We'll have a register write unit, and in the case of RW, we actually forward the RW result to three stages. So let me just go back and show the forwarding paths once again. So our forwarding paths are RW to OF, RW to EX, RW to ME. So RW is the biggest forwarder in that sense. It forwards to 3 stages. And MA to EX. MA to EX, we have already seen the forwarding path. We need to take a look at these three. So let's go to this path. So the register write unit, the value that it receives from the previous stages, the value that needs to be written into the register, the same value is forwarded to the OF, EX and MA stages via a forwarding path. So this is fairly simple. Some students might find it slightly difficult to understand it for the first time. As a reason, let's go back to the abridged diagram shown over here. So what we see is that so let's first the abridged diagram remains as it is. I have not shown the interlock units for reasons of simplicity, but the interlock units will also be there. So if I have forwarding, the only additional structures that I shall have is these blue multiplexers, and if you will count, there are 6 of them: 1, 2, 3, 4, 5 and 6. We added 2 multiplexers in the OF stage. The multiplexers choose between the value that's coming from the RW stage, right, the last stage, and the inputs generated by the register file. So you have this multiplexer and this multiplexer. In the EX stage, we add 3 multiplexers because EX receives forwarded inputs from 2 stages, from the MA stage and the RW stage. So each of these 2 multiplexers chooses between the default input coming from the previous stage and inputs coming from the MA and RW stages respectively. We need to add one more multiplexer for the store value, because the store value might be coming from the RW stage. So this chooses between the value, the default value and the value coming from the RW stage. Then in the MA stage, so MA stage is both a consumer and a producer of forwarded information. So the value it receives in the previous cycle can be forwarded to other stages, namely the EX stage. So we add this green line over here, which is a forwarding path. And the MA stage at the same time receives the forwarded input from the from the RW stage. So the RW stage's input goes here. So we choose, so in the case of a store instruction, not required in the case of a load, but in the case of a store, we choose between the default input and the input coming from the RW stage with the help of our 6th and last multiplexer. The results go to the memory system and we perform a load or store. Finally, we have a register write unit, and which does the work of the RW stage. We also send the value that we get from the previous stages, right? So we shall either get a value from the EX stage or a value from the memory unit in the case of a load. So whatever the value is, we send it to the rest of the 3 stages, OF, EX and MA, via the red forwarding path. So that is, so let me remove the annotation on this slide. So this is pretty much all the changes that we need to do to implement forwarding. And it's not much. So if you think about it, we have added 6 multiplexers to choose between the default inputs and forwarded inputs. The 6 multiplexers, I can have a laser pointer here. Yeah. So the 6 multiplexers are 1, 2, 3, 4, 5 and 6. Then we have a set of wires that come from other stages, and depending upon the logic we choose between one of the inputs, and that input is the input for the functional unit. That's all. Now let's take a look at forwarding conditions. So we need to determine if there is a conflict between 2 instructions in different stages. So a conflict means a read after write dependency. So we find if there is a conflict for the first operand, RS1 or RA, And we find if there is a conflict for the second operand, which is rs2 or rd in the case of a store, and for the first case, RA in the case of a ret instruction. So we will always, so let's assume that there is an instruction in the OF stage and it has a read after write kind of dependence or a conflict with instructions in all the three other stages, right? In the EX stage, in the MA and the RW. So basically for the same operand, we'll always choose the earliest we'll always, this statement is not actually correct. We'll always forward from the latest instruction. So, which basically means that if the instruction is coming from the EX stage, so let's assume that all the three instructions over here are, so this instruction is of the type add R1, R2 and R3, and all the three instructions over here are generating a value for R2. So we'll essentially forward from the EX stage because that is the latest stage, right? So EX stage is essentially overwriting the values of R2 produced by the two other stages. So we always forward from the latest instruction, that is before the current instruction. So let's take a look at the forwarding algorithm, which is very similar to the conflict detection algorithm. So let's look at the conflict on the first operand, which is RS1 or RA. So the input is the instructions A and B, and the possible forwarding is that instruction B is coming before instruction A. So B can forward some data to instruction A. So if a conflict if a conflict exists on RS1 or RA, we return true. Otherwise, if there is no conflict, we return false. So let's see. So since A in this case is a consumer instruction, and it is one of the following: NOP, BQ, BGT, call, not, and move. It means that it does not use its first source, right? So it does not use the first source operand. It does not use the RS1 field. And since it does not read from any register, we cannot have a conflict, so we return false. Similarly, if B is a part of this set, which is NOOP, CMP, store, B, BQ, BGT, and ret, it means that we are not writing to any register, so we cannot have a read after write kind of dependency when registers are involved, so we also return false. Otherwise, we set the sources. So we say that src1 is A's rs1 field. However, we take this special case into account that if A is a return instruction, then we set src1 as RA. So refer to chapter 8, we had discussed this special case. So refer to chapter 8 for this. Similarly, we set the destination. So in the case of we consider the destination variable. So mind you, this entire algorithm needs to be implemented in hardware. So we are only showing the pseudocode over here. So the destination register should ideally be the RD field in instruction B. However, if instruction B is a call instruction, then the call instruction writes to the return address register. So dest will be equal to RA. Once we have set the source and the destination, we need to detect conflicts. So if src1 is equal to dest, which means that the first source of A is equal to the destination of B, then a read after write kind of conflict on registers exists, so we return true, otherwise we return false. So let's look at a similar algorithm for the second source operand, which is rs2 and rd in the case of a store. So the inputs are instructions A and B, and there's a possible forwarding path from instruction B to instruction A. So a conflict will exist on the second operand rs2 and rd. If a conflict exists, we return true, otherwise we return false, similar to the previous algorithm. So let's do one more thing. Let's first look at instruction A. So if it's a part of this set, NOOP, B, BQ, BGT, so it's a branch instruction or it's a call instruction, This means that it does not read from any register. In specific, it does not use the second source operand of the register, source operand of the instruction. So since it does not read from any register, let's straight away return false. Now, let's consider instruction B. So again, if instruction B is a part of this step, this set, no op, compare, store, branch, different flavors of branches and return, it means that it does not write to any register. So we can also return false. Because if we are not writing to any register, we can't have a RAW dependence on a register. So we will also return false. Now let's see if the second operand is a register or an immediate. So let's do this little check, and we had done the same check for interlocks. So let's do it right now. So if A is not a store instruction, so why do we again say that A is not a store instruction? Because a store instruction by default has a second source, right? So store instruction has two sources pretty much. It does not have a register destination. And the store instruction has an immediate as well. So again, you can see that this is a consequence of the special case that was done for store instructions. So the moment we have special cases, we require a lot of logic in the pipeline to handle these special cases. So that's the reason special cases should be avoided as far as possible. But when we did make an exception for the store instruction, we didn't have a choice. So coming back, if A's immediate field is set to 1, this means that it does not have a second register source. So we can happily return false. So this means that the second register source, does not exist. Now that we have at this point ascertained that a second register source does exist, we set src2 to A's a.rs2, and if it's a store instruction, we set src2 to a.rt. Then we set the destination to b.rd, and what we had done in the previous slide, which is that in the previous algorithm, right, algorithm 6, is that if B's opcode is a call instruction, then we set the destination to the return address register. This is because the call instruction writes to the return address register. Henceforth, detecting conflicts is very, very easy. We say if src2 is equal to dest, then we return true, means a conflict exists. There is a read after write dependency with registers involved. Otherwise, we return false. So this was the algorithm for the second source register. Let us now look at the relationship between interlocks and forwarding. Because we will still require interlocks, so we'll still require a data log. So we'll require it to check for the load use hazard, right? So the load use hazard exists, which means that in consecutive stages, we have a load first, and then an instruction that uses the result of the load, an ALU instruction, an EX stage, which uses the result of the load, will have a load use hazard, so a stall needs to be introduced. The way we shall do this is that if the instruction in the EX stage is a load, and the instruction in the OF stage uses its loaded value, and it will use it also in the EX stage, right? Then we need to stall for one cycle. So this is the load use hazard. And so this is very easy to detect. We can use our same conflict detection circuitry to find the existence of a load use hazard, and then use the same circuitry to stall for one cycle. The branch lock remains the same as before, where we use option number 3, and if the branch is taken, we cancel, nullify, convert to bubbles the instructions in the IF and OF stages. So let's now take a look at the curious call of the call instruction. I have a burger over here. because there is some food for thought. So the call instruction generates the value of RA, the return address, in the RW stage, right? That's when we add PC equals, RA is PC plus 4. So any instruction that uses the value of RA, so you can always, nothing stops us from writing an instruction of this type, add R1 RA4, right? So any instruction that uses the value of RA such as ret or an instruction of this type, I can always define a code snippet of this type call.foo and ret. So any such instruction still works correctly. Why? Right? You need to prove it. So I think I'll give you an outline of the proof. So the call is a taken branch. So if call is a taken branch and I just draw a pipeline diagram, so what will happen is that in a given cycle, if the call instruction is over here, there will be no instructions, there'll be bubbles in the previous two stages, right? Bubbles in EX and MA. The reason being that it's a taken branch, so basically the two instructions immediately after it will get converted to bubbles. So the earliest point, the latest point at which instructions can be there is at this point. So here you can have an instruction which will use the value that the call instruction will produce, and this can use the RW to OF forwarding path, right? No problem in that. And since we are only adding PC plus 4, that's a very simple addition, it's a very fast addition. Then quickly do the addition and we can forward it from RW to OF. So any instruction which will be there, right, the closest it can come to a call instruction is it'll come into the OF stage. So it can get the value from the RW to OF forwarding path. As a result, it will get the correct value. So let's take a look at the complete data path again with forwarding and our pipeline in full blown glory. So this is the basic pipeline that we had, right? So we have gradually been building on it. We added our pipeline registers. Subsequently, we added our forwarding multiplexers, right? 6 of them. So the forwarding multiplexers have to be controlled. So the way we will do it is that all the pipeline registers will send information about their instructions to the forwarding unit. The forwarding unit will compute the control signals for all these multiplexers. I have not shown them, in the interest of readability, but pretty much there are lines from this to each of the multiplexers, right, to control it. Similarly, we'll have our data lock and branch lock circuitry exactly the way we had before. No difference in that. It is just that the data lock logic changes. It becomes slightly more simpler. That's the reason I have not taken inputs from the other two stages into the data lock unit. It's only the IFOF stage and the OFEX stage because this instruction and this instruction, these two matter for computing if there is a load use hazard or not. So that's the reason inputs have been taken only from these two registers, and the stall and the bubble circuitry remains the same. So just to summarize at this particular point, we have a fairly complicated processor on our screen. So it's a 5-stage pipeline. It's called a 5-stage in-order pipeline because instructions are not overtaking each other. They move in program order. And we have pipelining, we have interlocks, we have forwarding. Almost everything that is required to get a high performance in order implementation, right? In order processor implementation. So this is great. It's just that it's fairly complicated. So you will see in the website of the book that we at least are distributing the Logisim and VHDL models of the base processor. So it does not have pipelining and interlocks and forwarding. But normally, as assignments, we ask students to create a pipeline with interlocks, pipeline stages, and forwarding and they're able to do it. It's not a lot of work. So in a month or two, it's possible to do it, and it's a lot of fun. So I would advise all the readers and listeners, readers of the book and listeners of this video, that the right way and the most effective way of learning how to design a pipeline processor is to actually build one. So you can take a base processor that we have built in VHDL that does not have pipelining from the book's website, and then add pipelining to it. So it's a lot of fun. Alright, so now that we have seen forwarding, we can move on to the performance metrics of how to find out if a pipeline is fast or slow. So what do we typically mean by the performance of a processor, right? People will say one processor is faster than the other. So what do we mean by that? Well, the answer is almost nothing. So we should be asking a different question because there was a problem in our previous question. So we should be asking what is the performance of the processor with respect to a given program or a set of programs, because it is possible that processor A is fast for a certain program and slow for another program, and vice versa, right? Processor B is faster is for some set of programs and slower for another set of programs. So we should, ask these questions in the context of a, set of programs. Second, how do we define performance? So let us define performance very simply as a quantity that is inversely proportional to the time it takes to execute a program. So what we do is that we take a CPU, we take a processor, and we give it a program to execute, and simultaneously we start a stopwatch, right? So I'm a bad drawer, so hopefully this is showing a watch. So we start a stopwatch, and so the program starts and the program ends, and the total amount of time it takes, that is indicative of the performance of a processor. So the faster is the processor, the slower, the faster is the processor, the less is the time it takes to execute a program. And we essentially refer to performance as a quantity which is inversely proportional to the time it takes to execute a given program. So you will typically hear many other things, clock frequency and number of cores and so on. So performance is none of that. Performance is simply a quantity that is inversely proportional to the time it takes to execute a program. So if you want to compare processor A and processor B, then you take processor A and processor B, give both of them the same program to execute. The one that is faster has higher performance, the one that is slower has lower performance. So let's do a little bit of math and let's derive what is called the performance equation, which is very, very important. Is the crux of the entire pipeline math. So let us define the time a program takes as a number of seconds, right? So then let's do a little bit of very, very simple algebra. So let us say number of seconds divided by the number of clock cycles multiplied by the number of clock cycles divided by the number of instructions. So this is the number of instructions that the program actually executes on the pipeline, right? So let's assume this is the number of dynamic instructions. So let me just quickly differentiate between static and dynamic instructions. So assume there is a for loop, right? So it is possible that in the body of the for loop inside the binary of the program there are only 10 instructions. But if the for loop is running for 1,000 times, the number of instructions that the processor is seeing is 10,000, right? 10 times 1,000. So when we talk about number of instructions, we refer to this quantity. Is the number of instructions that the processor sees. These are called dynamic instructions. And then we multiply it by the number of instructions. So what we see is so it's a simple algebraic thing that we have done here. So the number of cycles will cancel out and number of instructions will cancel out. Oops, sorry, this should be multiplication over here. So number of seconds divided by number of cycles is actually 1 by the clock frequency, because the clock frequency is the number of cycles per second. So this is 1 by the clock frequency, 1 by f. So f comes in the denominator here. The number of cycles divided by the number of instructions is called the CPI, cycles per instruction. This is very important. And the number of instructions we'll refer to as num_insts. So pretty much the time that a program takes is CPI, the number of clock cycles per instruction, multiplied by the total number of dynamic instructions in the program that the processor sees, divided by the frequency. So as you can see, this is the time a program takes. It's not just the frequency, there are other variables. So let us define performance, which is a quantity which is proportional to 1 by the time. So performance is 1 by this, right? So we will say, so this will basically be f divided by CPI times number of instructions. Let us refer to 1 by CPI as IPC. IPC is instructions per cycle. So the performance will be proportional to IPC, instructions per cycle, times the frequency divided by the number of instructions. So this is a very, very important equation. It's very simple. It's very important, and most of the students get it wrong. That makes it even more important. And still, we will appreciate this equation in many of its forms, but let's at least try to memorize it for the time being. So this says that the performance of a processor with respect to a given program is the IPC, the number of instructions on an average that we execute per cycle, multiplied by the frequency, divided by the number of dynamic instructions in the program. So it's three quantities determine the performance, not one, but three. That's important to remember. And what are the units of performance? Well, they are arbitrary. So you can think of it as 1 by seconds, but it's not important. It's arbitrary. As long as the definition is being used in the same manner, it's being used consistently. Alright, so let's again remember the performance equation, which is performance is proportional to IPC, instructions per cycle multiplied by the frequency divided by the number of instructions. So the number of instructions, num_insts, let's see what determines it. So let us once again, for the benefit of the listener, differentiate between static instructions and dynamic instructions. So a static instruction is something like this. So the binary or the executable of a program will always contain a list of static instructions. So as we had shown in a for loop, if we have 10 instructions inside the for loop, right, then it's essentially 10. But now if the for loop runs for 1000 iterations, the total number of instructions that the processor sees is 10,000, and each 10,000 of them are dynamic instructions, which is pretty much a running instance of a static instruction. And this is created by the processor when the instruction enters the pipeline, right? So even if there are 10 instructions in the code of the for loop, if the for loop executes 1,000 times, the 10,000, 10 times 1,000, 10,000 instructions are pretty much being created by the processor. So a dynamic instruction, which is exactly num_inst, is the number of instructions that the processor actually sees. Right? So basically, how do we, have exercise some degree of control over dynamic instructions? Well, so the dynamic instructions are pretty much a function of, so dynamic instructions, with different kinds of pipelines and so on will still remain the same. It's a function of the code, right? So what do? We first write C code, which is converted to assembly code. And assembly code has a one-to-one correspondence with machine code. I'll just write MC to mean machine code. So a smart compiler can essentially reduce the number of dynamic instructions, right? The number of executed instructions by essentially generating code which is more compact. Instead of generating code which requires a lot of instructions. A smart compiler can do a lot of things to ensure that the generated code is fairly compact, and we also do not have dead code. For example, a lot of times programmers would write some pieces of code which are actually not used. So the compiler can remove all of that. That is one thing that the compiler can do. Other things that the compiler can do is, if let's say at any point some computation is being repeated, it can avoid that. So in a similar manner, when we are generating assembly code, where the compiler needs to keep in mind that reducing the number of instructions will actually really help us. So let's look at some of these schemes once again. So dead code removal means that programmers often write a lot of code which does not determine the final output, so it can run but it has no effect. So this code is redundant. So this can be identified and removed by the compiler. Often what programmers also do is they will create very small functions, and small functions have a lot of overhead. We need to call the function, we need to return from the function, we need to spill registers and restore registers. Instead of that, so for example, I can define a function of this type, right? Instead of that, it's a much better idea. So we can, write a piece of code which says y is equal to square of x. It is a much better idea to replace this with a code snippet which says y equals x times x. So we will be saving a call instruction, a ret instruction, many of these registers spill and restore instructions. And we'll be able to save a fair amount of code if we sort of remove this function and replace it with the logic of the function. So this is called function inlining, which means that we paste the code of the callee in the code of the caller. So compilers will do function inlining by default, and function inlining seriously helps us reduce the lines of code, especially lines of code which in a sense are not required. And programmers nevertheless do declare very small functions, and this has a performance overhead. And inlining will reduce it to a certain extent, and this is done automatically by compilers. Let's now take a look at the CPI. So the CPI for a single cycle processor is 1 because all instructions take 1 cycle to execute. Now let's consider the CPI for an ideal pipeline which does not have any hazards. So let's assume we have n instructions and we have k stages. So the first instruction enters the pipeline in cycle number 1, and it will leave the pipeline in cycle k because there are no hazards and thus no stalls. The rest of the n-1 instructions will leave in the next n-1 consecutive cycles. So the total number of cycles that we spend is n-1 plus k, because we spend the first k-1 cycles not doing anything, right? So for n instructions to pass through a k stage pipeline, it will take n plus k-1 cycles. And since there are n instructions, the CPI will be n plus k-1 divided by n. So this is also a very important equation and should be appreciated and understood to its full extent. Now the CPI in this case, if a pipeline has k stages, so let me maybe draw it in one more sense and show. So in the first cycle, if the first instruction enters the first stage, then at the end of the kth cycle, it will leave the pipeline. Subsequently, in every single cycle, one instruction will leave the pipeline. So then the total amount of time required will be n minus 1 plus k, same as n plus k minus 1. So CPI will be n plus k minus 1 divided by n. Let us now compute. So we have looked at the CPI. So what is the third component? It's the frequency. So let us let the maximum amount of time that it takes to execute any instruction within the processor be T max, and let us call this, refer to this as the amount of algorithmic work. So let us again assume that we will not, in the case of a single cycle pipeline, in the case of a single cycle processor, which has only pretty much one stage, we'll not divide the execution of an instruction into two clock cycles, right? Because we don't have a pipeline. So in this case, the minimum clock cycle time that we can afford is Tmax, because Tmax is pretty much the maximum time it takes to process a single instruction. So what will be the maximum possible frequency? Fmax will be 1 divided by Tmax. In the case of a pipeline, let us assume that all the pipeline stages are balanced, which means that they do the same amount of work. It takes the same amount of time to flow through them. So the time per stage and the total amount of work, that you do, the total time it takes for an instruction to finish its execution is Tmax. If there are k pipeline stages, the time per stage will be Tmax divided by k. Furthermore, so in pipelines, we have pipelines. So the typical structure is like this, that we have a pipeline register slash latch. Then we have some logic, and then again we have one more pipeline latch. So a pipeline register and a pipeline latch is the same thing. So pretty much the delay is the time it takes to pass through this logic, right? The logic can be an adder, multiplier, MA stage, OF stage, does not matter. And the delay of this, passing through the pipeline register. So let the latch delay be L. So as I said, in the case of pipeline, a pipeline register and a pipeline latch are the same thing. Otherwise, they're not the same, but we'll interchangeably use the term pipeline register and pipeline latch, or just a latch. So let the latch delay be L. So the time per stage is Tmax divided by K, which is the amount of work that you need to do in the logic part, right? Tmax by K plus L. So the minimum cycle time that you can afford is T stage. As a result, if you want to set the largest possible frequency, right, run the processor as fast as possible, we shall thus have 1 by f, right? T stage is equal to 1 by f, where f is the largest possible frequency at which you want to run the processor. So 1 by f will be equal to Tmax by k plus L. So let me explain this formula once again. So let us assume that in a single cycle processor which is not pipelined, the maximum time it takes for an instruction to go from the fetch part to the register write part is Tmax. Now if we divide this into k parts, the time per stage will be Tmax by k. Also, when we are dividing it into k parts, the division is not always perfect. So so basically the signal also passes through a pipeline latch. The pipeline latch has a certain delay associated with it, so let's refer to it as L. So the total delay is Tmax by k, which is the amount of time it takes for the instruction to pass through the logic part of the pipeline, and the latch, which is Tmax by k plus L. So if we assume, so this is the minimum time, it'll take for one instruction to complete one stage. So if we assume that our frequency is the maximum possible value as large as possible, we'll have 1 by f is equal to Tmax by k plus L, right? So this will give us the largest possible, highest possible frequency. So let us now work and find the performance of an ideal pipeline. So let us assume that the number of instructions is a constant, right? So it's a grammatical mistake over here. So let's assume that this number is a constant. So the performance, and let's also try to, in a sense, remove the proportionality sign just for the interest of readability. The proportionality sign is still there, but since we are removing number of insts from the equation, we are assuming that it's a constant for all kinds of pipelines. Because this is a function of the program, it has nothing to do with the pipeline. We will have the performance, well, equal to, this is some sort of taking a little bit of liberty here, should be proportional, it doesn't matter. So it is F divided by CPI or F times IPC. So the F that we have computed is 1 by T max by K plus L, and the CPI that we had computed is N plus K minus 1 divided by N. A little bit of algebraic manipulation gives us this expression, and a little bit of algebraic manipulation then gives us this expression. Let's keep going forward. So in this case, what do we see? We see that latch delay is here. N is the, so let's look at what these terms mean. L is the latch delay. T max is the algorithmic work or the total time it takes for an instruction to go from one end of the pipeline to the other. Let's call it the algorithmic work. K is the number of stages. That's all. And N is the number of instructions. So let us do one thing. Let's try to differentiate this equation with respect to K to find the optimal number of pipeline stages. So when we take a derivative with respect to K, this is the equation that we get, and this is the final solution that we get. This is the optimal number of pipeline stages. So as you see, in a pipeline with no hazards, the optimal number of pipeline stages is dependent on the number of instructions. So in fact, as the number of instructions tend to infinity, the number of optimal pipeline stages will also tend to infinity, which is not really a very practical thing, but since we have assumed an absolutely ideal pipeline, we are getting, very ideal yet unrealistic results. Also, the number of optimal pipeline stages in this case, the K, I would say K opt, right? K optimal is proportional to the square root of T max, square root of total amount of algorithmic work, and it is inversely proportional to the latch delay. So the higher is the latch delay, right? As the latch delay increases, the optimal pipeline stages actually decrease, right? And lower is the latch delay, we can have more pipeline stages. So given the fact that we have appreciated this, let us move to the case of a non-ideal pipeline which actually has hazards and interlocks and stalls and bubbles and everything. That will give us a much more realistic formula to work with, and we will use exactly the same methods of analysis. Before moving to a non-ideal pipeline, we'll just spend a quick half a minute discussing the implications of all the math that we did. So the first thing is that as we increase the latch delay, we should have, lesser pipeline stages, right? A lower number of pipeline stages. So this is because we need to minimize the time wasted in passing through latches, accessing latches. As we increase the amount of algorithmic work, we require more pipeline stages for ideal performance. This is because more pipeline stages will help distribute the work better and also consequently increase the overlap across instructions between instructions. The second is that as the number of instructions tends to infinity, the number of ideal pipeline stages also tends to infinity. And the higher startup time will get in a sense amortized in the long run. But again, this is for ideal pipelines, so let's quickly move to a non-ideal scenario. A realistic scenario. So ideal CPI ideal is 1 when you have no stalls. In reality, we do have stalls, right? So the ideal CPI is one, when number of instructions also tends to infinity, but in reality we do have stalls. So the CPI, the clock cycles per instruction, will be the clock CPI ideal, which in this case is 1, plus the stall rate. The stall rate is the number of stalls per instruction times the stall penalty, right? It'll simply be a weighted mean. And this is also a very important formula, which should be appreciated and in a sense remembered for later use. So this is trying to say that in any non-ideal processor, the CPI, or the clock cycles per instruction, is equal to CPI ideal. CPI ideal is basically the CPI on a pipeline with no stalls. So there, every cycle one instruction will come out of the pipeline. So since every cycle one instruction is coming out, this clock cycles per instruction. So assume that we have a k-stage pipeline, right? At the end of the pipeline, we have a person standing here. In an ideal pipeline, he would see that every cycle one instruction is coming out. So the person would compute the CPI ideal to be equal to 1. Now assume that there are some stalls. If there are some stalls, the person here can also find that given an instruction, what is the probability that it will suffer from a stall? That's point number 1. And point number 2 is that if it suffers from a stall, for how many cycles does it stall, right? So that's the stall penalty. So we need to make some assumptions here for a k-stage pipeline. So let's make some standard assumptions which have been made in other texts as well. So let us assume that the stall rate is a function of the program and its nature of dependencies. Let us further assume that the stall penalty is proportional to the number of pipeline stages. This is a reasonable assumption to make. The reason that we say that is because, if you have a 20-stage pipeline, for a load use hazard, we'll not stall for one cycle. We'll stall for some number of cycles which is proportional to 20, right? So we stall for one cycle in a 5-stage pipeline. But if we divide each of these single stages into 4 more stages, hopefully, we expect that instead of stalling for one cycle in a 20-stage pipeline, we might stall for 3, 4 cycles, right? Now it'll scale. So both these assumptions are strictly not correct in the sense they cannot be mathematically proven, but they are sort of empirically observed, and people think that it more or less correlates with what they have seen in real experiments, and it also correlates with their common sense. So we'll use this to make a mathematical model. So we'll say that the CPI is the CPI that we have observed before, which is n plus k minus 1 by n. So this is pretty much the ideal CPI where we're assuming that n is less than infinity for a small value of n. Because this number, as n tends to infinity, this number, as n tends to infinity, n plus k minus 1 by n will tend to 1, right? So let us assume that for small values of n, this will be, this does capture an ideal CPI. Furthermore, let R be the stall rate. So we are saying that the stall rate is dependent on the instruction. It is not dependent on anything else. And since it's dependent on the instruction, it will remain independent of the pipeline. So this is one constant. And we say that the stall penalty is C times K, where K is the number of pipeline stages, and C is a constant of proportionality. So as a result, the stall rate, which is again independent of the number of pipeline stages, and the stall penalty, which is proportional to the number of pipeline stages, Ck. So stall rate times stall penalty is Rck. So given this equation, let us modify our previous equation. So we are assuming P is equal to or is proportional to. So we're taking a little bit of liberty here. And since number of instructions remains constant in the design space, we have removed it from our equation. So F is still 1 by T max by K plus L, but the CPI equation has changed. So this is the additional factor that has come. So let us further do some algebra and simplify this expression. So we come here. Now let's again differentiate this with respect to k. If we differentiate this expression with respect to k, we shall get the optimal number of pipeline stages. So then after differentiation, we come to this expression. As n tends to infinity, we get the optimal number of pipeline stages, let's call it k opt, is equal to the square root of T max. T max is the algorithmic work divided by the latch delay multiplied by R, which is the stall rate, and C, which is the constant of proportionality for the stall penalty, right? Square root of T max by LRC. So this is the result that we get after all our algebra. And let's quickly try to appreciate what this equation is trying to tell us. So for programs, so let's look at the implications once again. So let me just write it once again. K optimal is square root of T max divided by LRC. Right? L is the latch delay, R is the stall rate, and C is the constant of proportionality for the stall penalty. So for programs with a lot of dependencies, a massive number of dependencies, will have a high value of R, right? High stall rate. We will need to use use less pipeline stages, right? Why is this case? Because we don't, so let's consider the pathological case where every instruction has a load use hazard with the instruction just before it, right? That is possible. So in this case, we actually don't gain much by heavily pipelining the processor, right? Pipelining only works when the number of dependencies between instructions are limited, such that we can take actual benefit of pipelining will accrue, and the number of bubbles that we'll introduce will be low. So that's the reason as we increase the stall rate, it calls for a reduction in the number of pipeline stages. Now for a pipeline forwarding, the stall penalty will be lower, much lower. So C is smaller than a pipeline that uses interlocks, right? Because in interlocks we are stalling for more cycles, for 3 cycles. For forwarding, most of the time we don't stall, and even if we do stall, in the case of a load use hazard, we stall for only 1 cycle. So C is smaller. So in this case, for a pipelining that is using forwarding, since C is smaller, the optimal number of pipeline stages will actually be more. So for a pipelining with forwarding, it makes sense to make it deeper. Deeper means add more stages. So it will require a larger number of pipeline stages to get optimal performance. Let me maybe summarize this. Forwarding implies have more stages. Alright, so let me once again write this expression. So the optimal number of pipeline stages is directly proportional to square root of T max by L. So the ratio of square root of T max by L, which is the total amount of work that needs to be done to process a single instruction, divided by the latch delay, is not really changing across technologies. So even as transistors get smaller, so look, as transistors get smaller, Tmax will reduce because smaller transistors are faster, right? So for an instruction to go from the beginning of the pipeline to the end of the pipeline, it will take a lesser amount of time. Simultaneously, latches are also getting faster, right? Roughly by a similar factor. So Tmax by L will remain the same. As a result, the number of pipeline stages will not change very significantly. So this explains why the number of pipeline stages has remained more or less constant for the last 5 to 10 years. Because Tmax by L remains more or less constant, R is anyway dependent on the nature of the programs, and C is a constant which also remains the same. So since over the years as transistors get smaller, It's only Tmax by L that we expected to see some change in, but that is also not changing. So it does not really make sense to increase the number of pipeline stages. So let us now do a little bit of math. So hopefully we have understood this. So I need to make another very, very important point at this point. So what is the real advantage of pipelining? The real advantage of pipelining, let's actually go back to this equation over here. So there are three factors in performance. One is the frequency. One is the IPC. So the performance equation can be thought of like this: that the performance is proportional to the frequency multiplied with the IPC divided by the number of instructions. So what pipelining allows us to do is it allows us to crank up the frequency. So it's Tmax by K plus L. So as we increase K in a certain, so we're decreasing the time per stage, and so then we can crank up the frequency. If the frequency increases, hopefully the performance will increase. But simultaneously, as the frequency increases and the number of stages increase, so this K over here is getting offset by a K in the denominator. So the IPC, there'll be an effect on the IPC. The IPC will most likely come down. But at one point, you'll have a maximum. So for a lot of papers which have plotted the performance in the y-axis versus the number of pipeline stages, what they have actually found is that at till one point, we can increase the frequency and we'll get higher performance. After that, the performance kind of decreases. So they choose the optimal point, and the optimal point gives us the optimal performance as well as the optimal number of pipeline stages. See, anyway, you can students can plot this equation and see, for representative values and how things change. So let's consider a typical math. So let's consider two programs where the fraction of loads is 0.4, 40% loads, 20% branches, and 50% of the branches are taken branches. Another program which has 30% loads, 10% branches, and 40% of the branches are taken branches. The ideal CPI is 1 for both the programs, and let 50% of the load instructions suffer from a load use hazard. Assume that the frequency of P1 is 1 and the frequency of P2 is 1.5. The units don't matter. So compare the performance of P1 and P2. So we will see many examples of this type where you're given an instruction miss, you're given the fraction of load use hazards, the frequencies of processor 1 and processor 2, and let's compare the performance. So we know that the CPI new, right, the CPI is CPI ideal plus the stall rate times the stall penalty. So we will see take the ratio of loads, multiply them with 0.5 because half of the loads suffer from a load use hazard. So this is the ratio of loads that have a load use hazard. So this is pretty much the stall rate. Multiplied by the stall penalty for a load use hazard is 1 cycle. Plus the ratio of branches multiplied by the ratio of taken branches within that. So this is the stall rate for branches multiplied with the stall penalty, and the stall penalty for taken branches is 2 cycles. So we compute the CPI by taking values from the previous table. We find the CPI of P1 to be 1.4 and the CPI of P2 to be 1.23. So the performance can be expressed as a quantity which is F divided by CPI, which is 0.71 for P1. Units are arbitrary. Similarly, the performance of P2 is equal to F divided by CPI, which is 1.5 by 1.23, which is 1.22. Since the performance of P2 is higher, we can say that P2 is faster than P1. So we shall often use the term, and for arbitrary units, we'll use the term AU when the units don't matter, right? But what is the most important takeaway point from this slide is the way that we compute the CPI. So CPI is CPI ideal plus stall rate times stall penalty. So the stall rate is that per instruction, what is the probability that you'll have a stall? And so there can be multiple reasons for a stall, right? So you can have stalls because of loads, you can have stalls because of branches. They are disjoint events, so we can put a summation here. So for the case of a load, we observe that given an instruction, let's say ratio loads tells us that for every instruction there's a probability of 0.4 that it's a load. And for every load there's a probability of 0.5 that it will lead to a load use hazard. So the total probability that given an instruction it will lead to a load use hazard is 0.4 times 0.5, which is 0.2. And the stall penalty for a load use hazard is 1 cycle. So we get stall rate times stall penalty for loads as this expression. Similarly, for branches, we need to find what percentage of the instructions are branches, and out of the branches, what percentage are taken branches. That will give us the stall rate because for every taken branch we stall, and we'll get the stall penalty. The stall penalty is 2 cycles per taken branch. So when we multiply both of them, we'll get the number of stall cycles for taken branches. So when we add all of these components, we'll get the CPI new. And subsequently getting performance is very simple because performance is proportional to F divided by CPI when the number of dynamic instructions are the same. Alright, so let's take a look at these factors once again. We have in a sense performance is equal to, well, we have been slightly taking some liberty, should technically be proportional, but we have been taking some liberty, let's keep on taking it. So performance is pretty much F times IPC divided by number of instructions, but number of instructions is completely dependent on the compiler. So I have sort of taken it out of this particular expression. Oops, sorry. So the frequency is dependent on several things. So what is the frequency? So frequency we said is 1 divided by Tmax by K plus L. So it's dependent on the algorithmic work, which is the time an instruction takes to go from the beginning of the pipeline till the end, divided by the number of pipeline stages plus the latch delay. So Tmax and L are completely dependent on the way that the circuit is made and the speed of transistors, right? So this is pretty much dependent on the transistor technology and the circuit. Transistor plus, transistor plus circuit technology. The other factor in determining the frequency is K, which is the number of pipeline stages, and this is determined by the architecture, right? The way we design the chip, the computer architecture of the chip, that determines the factor K. So as we see that the frequency is determined by the technology, the transistor technology, in terms of Tmax and L, and K is determined by the architecture, right? So Tmax and L from the technology and K from the architecture. Similarly, when you talk about IPC, which is 1 by CPI, it is of course determined by the compiler because you can order the code in such a way that there are no load use hazards, right? Can be done. So compiler has a role to play. The architecture definitely has a role to play because look, schemes like forwarding are architectural schemes. Interlocks and forwarding are architectural schemes. There are many more architectural tricks that can be done to ensure that our stall rate and our stall penalty go down. So these determine the IPC of the processor. And so the IPC is definitely determined by the architecture, and the strongest The most potent IPC increasing mechanism that we saw in this lecture is forwarding. So what does forwarding do? Forwarding essentially reduces the number of stalls. So it reduces the CPI and it increases the IPC. We have the other factor, which is the number of instructions, and the number of instructions is dependent purely on the compiler. And so basically we have three things. We have the technology, we have the architecture, and we have the compiler. And it's the interplay of these three that determine the performance. And here again, I would like to state the most important thing which almost all students miss, that where does the benefit of pipelining come from? So it clearly does not come from the number of instructions because this is a function of the program, right? So the benefit can't come from here. The benefit cannot come from IPC. I'll tell you why. Because let us consider, so what is the IPC of an ideal pipeline? The IPC of an ideal pipeline, the number of instructions per cycle of an ideal pipeline for a person who's standing over here, assume that this is the end of the five-stage pipeline, right? For an ideal pipeline, one instruction will be coming out every cycle. So this person will see the ideal IPC to be 1. So I can say that the IPC ideal is 1. And what is the IPC of a single cycle processor without any pipelining? Well, every instruction is completed in a single cycle. So the CPI is 1 and consequently the IPC is 1. But in any real pipeline which will have hazards and stalls and bubbles, the IPC is expected to be less than 1, right? Because we will actually have stalls, right? So we need to stop. We can't process every instruction in one cycle. We have dependencies. So the number of instructions remains the same. It cannot be a factor. IPC decreases. So it definitely cannot be a factor. The only factor that is responsible for increasing performance is frequency, right? So let me delete the ink on this slide because I want to make a very important point. The only factor which, one second. Yeah, the only factor which allows us, right? So basically we know that, in this equation, in this particular equation, there is nothing that is really helping the case of pipelining. Number of instructions aren't, IPC is not. The only advantage we are getting from pipelining is that we can reduce Tmax by K by increasing the number of pipeline stages. So if we increase the number of pipeline stages, we can increase the frequency. And it is only this factor which is giving us the benefit that if we increase the number of pipeline stages, we will reduce the time per stage. As a result, we can increase the frequency. And by increasing the frequency, we'll be increasing one term in the performance equation. The IPC will maybe slightly decrease as we have been seeing, but that's okay. As long as the product increases, we are just fine. And so that's the advantage. The advantage of a pipeline, listen to this very carefully. The advantage of a pipeline is that it allows us to increase the frequency. When we increase the frequency, the numerator of the performance equation, one term of the numerator of the performance equation increases. And as we increase the frequency, we need to increase the number of pipeline stages also. Ultimately, that will have negative effects in terms of IPC. As a result, we can't increase the frequency arbitrarily high, but frequency will definitely, from our math, the optimal frequency will be 1 divided by Tmax divided by K optimal, which is the 1 square root of Tmax by LRC. Plus L, right? So we'll have an optimal frequency at which the performance peaks. So if let's say I plot, the number of pipeline stages or the frequency versus performance, I will see, some graph like this where there is an optimal frequency at which the performance is highest, and this is exactly what pipelining allows us to do. We can keep on increasing the frequency till some point, and we'll get higher and higher and better performance. And that's the advantage. Now let's say that we are not allowed to increase the frequency because somebody will say that this is not something that a transistor can support, or the power dissipation will become very high. So then the natural limits are placed on increasing the frequency. But still, if we are pipelining a processor and we don't increase the frequency, we are not going to get any performance benefit. The performance benefit only comes by increasing the frequency, and that's the crux of the pipelining idea. That if we don't increase the frequency after pipelining a processor, we get nothing in terms of performance. Only when we increase the frequency, we get something. There are, of course, limits to how much we can increase the frequency to. Even if, let's say, from this expression it comes out that the optimal number of pipelining stages is 20, there might be other constraints on why we can't have that deep a pipeline. And also the power that a processor dissipates is actually proportional to V square, which is V is the supply voltage times frequency. Right? So as we increase the frequency, the power dissipation increases. So this is also a problem. We can't have processors that dissipate a lot of power. So this places limits on the frequency, and placing limits on the frequency places limits on the number of pipeline stages that we can support as well. That's one reason why, at least over the last 10 to 15 years, the number of pipeline stages have remained roughly constant between 10 and 15, and the frequency has also remained roughly constant between 2 and, let's say, 3.5 gigahertz. All right, so let's finish this, very interesting discussion on pipelines. So this current lecture ends here. The last part, the fourth part of this lecture series, will look at advanced topics on how to handle interrupts and exceptions. So that will be the last part of this lecture series.